Hello everyone, my name is Beck. I'm from China and I'm in 11th grade. My intended major is statistics. I'm very happy to have this chance to present my project on Polygence Symposium. Let's cut to the chase then. My topic is NBA regular season wins prediction based on new metrics in machine learning. Here are the contents of my project. First, we have overview. Second, we have introduction, where we spot the mistakes of traditional metrics. Third, we have methods. We will talk about new metrics I invented and modeling. Fourth, conclusion. This includes results and discussion. Overview. Let's introduce the player efficiency rating, PER, and Pythagorean wins, PW first. PER is an advanced basketball statistic created by John Hollinger. It's designed to assess a player's statistical accomplishments. PER takes into account a player's positive contributions, such as points, rebounds, assists, and steals, and negative actions like missed shots, turnovers, and personal fouls. In addition, PER is adjusted to the pace of the season and thus can compare players from different eras. This allows for a comprehensive evaluation of a player's overall efficiency on the court. Pythagorean wins is a metric that estimates the team's expected wins based on its points scored and allowed over a given period. The fundamental premise underlying PW asserts that a team's winning percentage can be approximated using a formula derived from the Pythagorean theorem. The accuracy of PW is extremely high. However, these two prevailing advanced metrics in the NBA all have some mistakes. PER unreasonably favors players who make less mistakes, even when they don't make much contribution, and players who play in a slow-paced team. PW offers unbelievable accurate predictions, but makes the mistake of data leakage. We will talk about these two metrics and their mistakes in more detail in the following part. Inventing new metrics. The principle of choosing predictors is the non-existence of data leakage. Data are defined into two categories, one indicating production and the other reflecting efficiency. The fundamental idea is that the higher a team's production, the harder it is to maintain efficiency. The ability of maintaining efficiency should be considered in team evaluation. We multiply team's pace by 0.01 and divide opponent's pace by 0.01 as adjuster and opponent's adjuster to take the team's production level into consideration, while do not risk data leakage because there are still efficiency data. Pace represents the number of offensive possessions a team has per 48 minutes, which is the regular game type, and serves as an efficiency metric that reflects a team's offensive tempo. Testing results validated by for machine learning models. They are GBM, KNN, random forest, SVR. We'll talk about them later. The application of these metrics, particularly random forest and gradients boosting machine, has demonstrated significant improvements in predictive accuracy and stability. From the include purity plots in random forest and feature importance plots in gradients boosting machine, we noted that the relative differences in the same metrics between teams and their opponents contribute more to the model than the metrics themselves. Among them, the difference between adjusted field goal percentage contributes the most to both models. Okay, this is the introduction part. As we can see, the title of this page is Unfair PER. Why PER is unfair? Let's look at the following example in a specific season. Player A drops 27.5 points, 6.3 rebounds, 3.8 assists, 3.9 steals, 0.8 block, 2 points, 2 turnovers, and has a 52.9% of two field goal percentage and 38% of 3-point field goal percentage in every 36 minutes. Player B drops 25.2 points, 8.2 rebounds, 8.3 assists, 1.2 steals, 0.6 blocks, 3.9 turnovers, and blah, blah, blah. We conclude that the player B is the more versatile player, as we can see from the radar charts. The green chart is player 2, and the pink picture is player 1. So from the radar charts, our intuition is obviously right, that B is a more versatile player. However, PER, the advanced metric of comprehensive evaluation of players, favors player A to player B. In fact, player A is Kawhi Leonard. Player B is LeBron James. Both data is collected from season 2016 to 2017. What's wrong with PER? Here is another example in the season 2023 to 2024. AO drops those points, those rebounds, those assists, and Bogdan drops those points, those rebounds, those assists, blah, blah, blah. In this season, AO has a PER of 13.3 and Bogdan has a PER of 14.8. The difference of their PERs is 1.5. Let's have a look of their basic stats from radar charts. You can see there's also only slight difference between their stats, and such a difference in such a small difference in basic stats is enough to result in a difference of 1.5 in PERs. However, let's compare Russell Westbrook's performance in season 2014 to 2015 to that in season 2016 to 2017. It is clear from the radar charts that Russell has much better performance in season 2016 to 2017 than season 2014 to 2015. But surprisingly, PER of Russell in season 2016 to 2017 is 30.6 and 29.1 in season 2014 to 2015. The difference in Russell's PER is exactly 1.5, the same as that of AO and Bogdan in the middle picture. It seems that the progress made by Russell in PER does not match the progress in his stats. What's the relative disadvantage of Russell? We spot his relative higher turnover rate and lower shot percentage than AO and Bogdan. However, there's mainly because Russell shoots a lot more than the former. Russell made 842 baskets in season 2016 to 2017 and 647 in season 2014 to 2015. By contrast, AO made 339 baskets and Bogdan made 428 baskets in season 2023 to 2024. In the basketball world, no player can make a higher shot percentage with more shots attempted. In conclusion, players who make less mistakes are unreasonably favored by PER. They have higher PERs than players who have more versatile data but more make mistakes. The current predictive metric of regular season wins is Pythagorean wins. This metric estimates the team's expected wins based on its points scored and allowed over a given period. The fundamental premise underlying PW asserts that a team's winning percentage can be approximated using a formula derived from the Pythagorean theorem, formally expressed as here. P represents an exponent, typically around 13.91 for basketball. The accuracy of PW is extremely high. We can tell it from its MAE, which is mean absolute error. That means it has an error of 2 games. That is very, very accurate to regular season wins prediction. The results indicate that the average prediction error of PW is 2.37. Since PW is already so accurate, why attempt to predict the number of wins? However, that's because the mistakes of Pythagorean means, which is data leakage. Data leakage refers to the situation where information from outside the training dataset is used to create a model. This can lead to overly optimistic performance estimates during model training and evaluation. For example, it's risky to provide models points data because the team who wins the most probably scores the most points. To avoid data leakage, we should not use production data, especially scoring related data such as 3PM, which directly influence team scoring. For instance, teams with higher 3PM scores more 3-pointers, increasing their total score and the likelihood of winning games. By contrast, only efficiency data, such as three points percentage and offensive rebounding rate, should be used as predictors. This approach helps mitigate the risk of data leakage. So through the PW formula, it can be seen that PW calculations are directly based on total points scored by the team and total points allowed, which fall under production data. This poses significant risk of data leakage. We can see again the formula of Pythagorean means from here. Using the same logic, we must also discard true shooting percentage, margin of victory, strength of schedule, offensive rating, those metrics, because they directly use win losses records or the total points of the team. Methods. The fundamental premise of this research posits that in basketball, as in any sport, a higher level of team production typically correlates with increased difficulty in maintaining efficiency. Therefore, the capacity to sustain efficiency should be a critical criterion in team evaluation. The primary metric under scrutiny is pace, defined as the number of offensive possessions a team has per 48 minutes. Pace serves as an efficiency metric that reflects a team's offensive tempo. This approach mitigates the risk of data leakage while accounting for the team's production level. Typically, a team's pace value fluctuates around 100, representing the average number of sessions per game. To normalize this metric, we apply an adjustment factor of 0.01 times the pace, resulting in a value close to 1. Additionally, we create an opponent's adjustment factor, OPP adjuster, which is 0.01 times the opponent's pace. These adjusters are employed as multipliers or divisors to refine the team statistics, accounting for the ability to maintain efficiency. We anticipate that these adjustments to lead to more precise predictions of team performance. I'll name some examples of how the formula is made. For adjusted offensive rebound percentage, the more offensive possessions the team has, the harder it is to maintain a high offensive rebound percentage. The adjusted ORB percentage should be higher than its actual value for a fast-paced team and vice versa, so it's multiplied by ADJ adjusters. For adjusted turnover percentage, the more offensive possessions the team has, the harder it is to maintain a low turnover percentage. The adjusted turnover percentage should be lower than its actual value for a fast-paced team and vice versa, so it's divided by adjuster. For adjusted steal percentage, the more offensive possessions the opponent's team has, the harder it is to maintain a high steal percentage. The adjusted steal percentage should be higher than its actual value for a team who plays against fast-paced opponents and vice versa. So it's multiplied by opponents' adjusters. Here is the most important new metric, adjusted field goal percentage. This metric incorporates FT free throw percentage, 2 points field goal percentage, and 3 points field goal percentage. The core idea is to take the respective points values and counted attempts for 3-point shots, 2-point shots, and free throws into account. Each 3-point attempts and 2-point attempts are counted as one field goal attempt, and each free throw attempt is counted as 0.44 field goal attempts, according to John Hollinger, because free throws also take up possessions. Firstly, the equivalent 2-point field goal percentage are calculated for the team's 3 points, 2 points, and free throw percentages based on their points values and attempts counts. Next, the harmonic mean of this adjusted equivalence percentages is computed, eliminating the need for a weighted harmonic mean since the percentages have already been weighted. It is important to note that the maintaining a high field goal percentage becomes increasingly challenging with the higher number of offensive possessions. Therefore, the adjusted field goal percentage should be higher than its actual value for teams with a fast-paced style and vice versa. Consequently, the harmonic mean is multiplied by an adjustment factor to reflect this dynamic. Initially, the model is trained using a dataset constructed with new metrics, and its mean absolute error (MAE) is obtained. MAE is used here because the highest regular season win record in NBA history is 73 by Golden State Warriors, which is not considered an outlier, thus eliminating the need for mean squared error (MSE). The model is then trained using a dataset constructed with traditional data, and its fitting accuracy is obtained. Finally, the natural logarithm of the ratio of the accuracy from the two training sets is computed to evaluate the model's improvements. To visualize these improvements, a grouped bar chart can be plotted. It is important to note that the lower the MAE, the more accurate the model is. The machine learning models we choose are K nearest neighbor regression, random forest, gradient boosting machine, and support vector regression. We conclude that based on new metrics, random forest, K nearest neighbor regression, and gradients boosting machine significantly reduced the error. Surprisingly, the error in SVR slightly increased for the new metrics, but the difference is not small enough to be negligible because the relative change in MAE is the natural logarithm of the changes. Also, we have to conduct a stability test for a comprehensive evaluation of the model. This involves determining potential overfitting risks, reducing the sample size. By reducing the sample size, the models are retrained and tested using half of the previous year's test and training data, maintaining the chronological order to ensure the integrity of the prediction process. The relative change in model accuracy is represented by the natural logarithm of the MAE ratio. In this context, a lower relative difference in MAE indicates greater model stability. Based on their accuracy and stability, the four models are evaluated, and the final choice is made. From the plots, KNN regression turns out to be extremely stable. Gradient boosting machine and random forest demonstrates relatively high stability as well. However, for SVR, this unfortunately shows a bad stability, with its MAE increasing from 5.6 to 7.3. Conclusion. From the bar plots of models MAE trained on new metrics and the relative change in MAE in the stability test, we can do our model evaluation now. KNN regression proves to be the most stable model, but shows a very low accuracy. Random forest achieves the highest prediction accuracy and has stability with a negligible difference with GBM stability. GBM shows high prediction accuracy and second highest stability. supports vector mesh regression. SVR demonstrates high prediction accuracy, but its stability is much lower than other models. In summary, the random forest model is selected as final model for predicting NBA regulars in the mean. Nevertheless, the gradient boosting machines analysis is also considered due to its high quality accuracy, and stability. The ink node purity plot demonstrates the contribution each feature makes to the random forest model's predictions. The higher the ink node purity, the greater the feature's contribution. The most notable feature in the charts is that the relative differences in the same metrics between teams and their opponents contribute more to the model than the metrics themselves, except for adjusted turnover rates, whose ink node purity is almost equal to its ratio. This is reasonable because victory requires outperforming the opponents. Specifically, the more significant contribution is from adjusted field goal percentage ratio, indicating that the key to winning lies in the difference in overall shooting efficiency between the two teams. Here, overall also considers the team's pace and the proportion possessions taken by free throws. Next is pace ratio, showing that the number of possessions per unit time for both teams affect win prediction. Possibly because differences in pace greatly impact the team's regular tactics and its stamina distribution. The third most significant contributor is the adjusted assist percentage, highlighting that smoother team cooperation and offense compared to the opponent significantly contributes to the winning in modern basketball. The fourth is adjusted steal rate ratio, reflecting a team's strong defensive style compared to blocked steals can directly lead to a transition from defense to offense, clearly disrupting the offensive rhythm and team coordination of the opponents. Given the significant drop in the ink node parity between the fifth and fourth values, contributions beyond the fourth ranked value are not high. Therefore, we provide partial explanations for only a few values under the fourth rank. Without considering the relative differences between the team and opponents, the adjusted field goal percentage is just a numerical value, but maintaining a reasonably high shooting percentage is more crucial than controlling turnovers and rebounds for winning a game. Offensive rebounds and defensive rebounds rates have low contribution values, possibly because they are not necessarily related to shooting efficiency and team cooperation, or have minimal impact on the opponent's pace. Given the high contribution value of the adjusted steal rate ratio, a potential explanation for the lower ranks of the adjusted TOV percent and ATOV ratio is that the proportion of turnovers not caused by the opponent's steals is relatively high, leading to a lack of proportionality between steals-related and turnover-related data. Additionally, adjusted steal rate reflects strong team defense, while turnover rate is neither a defensive efficiency indicator nor necessarily related to low overall shooting efficiency. Then we plot the relative influence of features in the gradients boosting machine model to see if there are any discrepancies compared to the ink node purity in the random forest model. In the gradients boosting machine model, the ratios of the team's metrics to their opponent's metrics continue to have a greater impact than the metrics themselves. The feature with highest relative influence remains adjusted field goal percentage ratio. Both adjusted assist percent ratio and adjusted steal ratio are still among the top four contributors. The contribution of pace ratio has decreased compared to its significance in the random forest model, but remains relatively high. Adjusted turnover percentage ratio continues to be the least impactful among the ratio metrics. However, unlike in the random forest model, adjusted offensive rebounds percentage has a high relative influence in the gradient boosting machine model, whereas it was less important in the random forest model. In summary, with a few exceptions, the feature importance, rankings in the random forest and gradients boosting machine models are nearly identical. This consistency further validates our analysis and underscores the significance of these features in predicting victories. Summary: this research has introduced a novel approach to NB-even prediction by developing new efficiency metrics that mitigate data leakage issues inherent in traditional metrics like PER and PW. By incorporating adjustments for team pace and opponents comparisons, our proposed metrics offer a more nuanced evaluation of team performance. The application of these metrics in machine learning models, particularly random forest, has demonstrated significant improvements in predictive accuracy and stability. The findings highlight the critical role of efficiency-based metrics in enhancing the reliability of NB-even predictions. These metrics provide a comprehensive assessment of team performance, offering valuable insight for coaches, analysts, and management in their strategic decision-making processes. The enhanced predictive accuracy achieved through these metrics underscores their potential to revolutionize performance evaluation in professional basketball. That's all. Thanks for watching.